Imagine something out there lurking in space. Something so powerful it could actually destroy Earth without any warning at all. And, well, it could be headed our way right now.
Sounds a bit like science fiction, doesn't it?
It really does. But, this isn't fiction. It's science fact. Welcome to the Deep Dive.
Today we're taking a look into the pretty unsettling reality of rogue black holes.
Yeah, we've pulled together some fascinating and maybe a little unnerving science about these, well, invisible galactic threats.
We're drawing on the latest scientific understanding, really trying to get a handle on their nature and what they could potentially do.
Right. So our mission today, for you listening, is to really understand what these things are. Rogue black holes, how scientists try to spot them sometimes.
And the dangers they might pose, if one wandered nearby.
And crucially, what's the current thinking on whether one might actually be on its way? The idea is to arm you with knowledge, not overwhelm you with fear.
Exactly. Let's get into it.
Okay. So first things first, what exactly are rogue black holes?
Right. So most people, when they think black hole, they picture the supermassive ones at the center of galaxies, like our Milky Way's Sagittarius A.
Or maybe the smaller ones left over when a giant star collapses, right?
Precisely. And that's where most black holes are found. But these rogue ones, they're different. They're essentially galactic castaways.
Castaways, you mean they've been kicked out of their home galaxy?
Yeah, exactly. Ejected. Usually by some pretty violent cosmic event.
Like what kind of event?
Well, think about huge events like galaxies colliding. That kind of massive gravitational disruption can do it.
Okay.
Or even complex gravitational interactions within a dense star cluster, like a sort of gravitational slingshot. It can just fling a black hole right out into intergalactic space.
And these aren't moving slowly, I gather.
Oh, not at all. We're talking speeds up to potentially 5 million miles per hour. Just incredibly fast.
5 million miles an hour. That's hard to even grasp. And the kicker is, they're invisible.
That's the really tricky part. They don't emit light. No glow, no radiation we can easily pick up. They're just dark matter drifting through the void, silently.
Okay, so that leads straight to the obvious question. If they're invisible, how do we even know they're out there? It seems impossible.
It's a huge challenge, absolutely, but not completely impossible. One of the main methods we use relies on gravity itself. It's called gravitational lensing.
Lensing. Like a lens bending light.
Exactly like that.
Yeah.
Because a black hole has such intense gravity, it actually warps the space-time around it. So if a rogue black hole passes directly between us and a distant star,
the light from that star gets bent.
Precisely, gets bent around the black hole. From our perspective here on Earth, we see the background star momentarily brighten or its image distort in a very specific, characteristic way.
So we don't see the black hole, but we see its effect on the light behind it, like seeing ripples on water without seeing the stone that dropped in.
That's a great analogy, yes. It's indirect detection. And NASA, using instruments like Hubble, has found evidence for several potential rogue black holes this way.
And didn't one pass relatively close? I remember reading something like 3,000 light years away.
That's right. There was a candidate event suggesting a black hole passed about that distance. Now, 3,000 light years is still immensely far in human terms.
But cosmically speaking, that's practically next door.
Well, maybe more like down the street in a very large city. But yes, on a galactic scale, it's relatively close.
Does this lensing always work, though? Or could some just slip by completely unnoticed?
Oh, absolutely. Lensing requires a very precise alignment. The black hole, the background star, and us. It has to line up just right.
So for everyone we might detect by chance.
There could be many, many more out there that we just don't see because the alignment isn't right. We're likely only seeing the tip of the iceberg, assuming they exist in the numbers estimated.
Okay, let's shift gears into the what if. This is where it gets a bit more intense. What happens if one of these things doesn't just pass by, but actually enters our solar system?
Right. Well, the consequences would depend heavily on how close it came. Even a relatively distant pass could cause significant disruption.
Oh, so just by its gravity.
Yes. Its immense gravity would tug on everything. The sun, the planets. The delicate balance of orbits we have could be thrown completely out of whack.
So Earth's orbit could change?
It could. It might be stretched out, making seasons drastically different. Or tilted. Or in a worst-case scenario, Earth could even be, well, ejected from the solar system entirely.
Flung out into the cold darkness of space.
Wow. Or potentially nudged closer to the sun. Neither is a good outcome.
Okay, that's just the orbital mechanics.
Yeah.
What about other effects? I saw mentions of stripping away our atmosphere. Strange glows in the sky?
Yeah.
That sounds terrifying.
Yes, that's if it gets closer still. A close encounter, even without a direct hit, could exert powerful tidal forces.
Tidal forces. Like the moon, causes ocean tides, but much stronger.
Much, much stronger. Strong enough to potentially pull the upper layers of our atmosphere away from the planet.
And losing our atmosphere means?
A huge increase in deadly radiation reaching the surface. Plus, the interaction of that intense gravity and radiation with the remaining atmospheric gases could ionize them, causing them to glow in unusual ways. So yes, strange, eerie glows in the sky are plausible.
Okay, but the ultimate nightmare scenario is a direct hit or getting really, really close. Let's talk about spaghettification. It sounds almost funny.
It does, but the reality is anything but. Spaghettification describes the extreme stretching effect of tidal forces near a black hole.
How does that work?
Imagine Earth approaching the black hole. The gravitational pull on the side of Earth facing the black hole would be immensely stronger than the pull on the far side.
Okay, a huge difference in pull across the planet.
An enormous difference. This difference in force would stretch the entire planet vertically along the direction of the black hole, while simultaneously squeezing it horizontally.
Like stretching spaghetti, hence the name.
Exactly. The planet would be drawn out into a long, thin stream of atoms and matter.
And then what? A huge explosion.
No, that's one of the chilling things. There'd be no Big Bang, just this incredible silent stretching and distortion.
Oh no.
And then Earth, as a recognizable planet, would simply cease to exist. It would be pulled across the event horizon, the point of no return, and vanish, silently, into darkness.
That is profoundly disturbing. Just silence and gone.
Yeah.
Okay?
Yeah.
Deep breath.
It's a difficult concept to grapple with.
So the $1 million question, or maybe the 100 million black hole question, is there one heading for us right now? Should we be worried?
Okay, let's be clear. As of right now, there is absolutely no confirmed rogue black hole on any kind of collision course with Earth or our solar system. Zero evidence for that.
That's reassuring.
Ish, yes. Because while there's no known threat, the estimates suggest there could be a vast number of these things wandering the Milky Way.
What kind of numbers are we talking?
Some estimates put the number around 100 million rogue black holes just in our galaxy alone.
100 million. Invisible, super dense objects hurtling around.
That's the estimate, yes. It comes from calculations about star formation, galaxy collisions, and how many black holes are likely formed and subsequently ejected over cosmic history.
And we can only detect them by that chance alignment for gravitational lensing.
Pretty much. Or if they happen to accrete matter, which would make them glow, but a lone black hole in empty space wouldn't necessarily be doing that. So detection is very difficult.
And they're moving fast. So if we did detect one coming close, how much warning would we get?
That's another unsettling aspect. Because they move so rapidly, even if we detected one through lensing when it was relatively nearby, astronomically
The
speaking,
warning time might be short.
it could be quite short, potentially just months or maybe even only weeks or days, depending on the trajectory and speed. Not a lot of time to, well, do much of anything, frankly.
Right. That really puts the scale of the universe and our ability to track things into perspective, especially the invisible things.
It certainly does.
Okay, let's maybe lighten the mood slightly, if possible, with some of the fun but still kind of creepy black hole facts that came up in the research.
All right, let's try.
I was blown away by the idea that some black holes could be the size of an atom but have the mass of a mountain. How does that even work?
It comes down to density. All that mass is crushed down into a point of theoretically infinite density called a singularity. So the size we often talk about is the event horizon, the boundary, but the actual mass is packed incredibly tightly.
So an atom-sized object with mountain-level gravity. Mind-bending.
It really warps space-time in its immediate vicinity.
And speaking of mass, what about TON 618? This thing is apparently 66 billion times the mass of our sun.
Yes, TON 618 is one of the most massive black holes ever discovered. It's a supermassive black hole at the center of a distant quasar. It's truly immense.
Makes you feel rather small, doesn't it?
Puts things in perspective, absolutely. Though rogue black holes are generally expected to be stellar mass, maybe a few times the mass of the sun, up to perhaps a few dozen, not billions.
It's still significant. Then there's the time dilation thing. Time slowing down near a black hole, even potentially pausing.
Yes, a classic consequence of Einstein's general relativity. Gravity warps space-time, and time is part of space-time.
So stronger gravity means slower time.
Exactly. The stronger the gravity, the more time slows down relative to an observer far away. As you approach the event horizon, this effect becomes incredibly extreme.
Could you actually pause time?
Well, theoretically, time would appear to stop at the event horizon from an outside observer's perspective, but for someone falling in, time would continue, albeit leading to, well,
Right, leading back to spaghettification. Can't seem to escape that lovely image.
it's the inevitable outcome. If you cross that boundary for a stellar mass black hole, yes, those tidal forces are just too extreme.
So let's try and synthesize this. What are the actual survival chances if Earth encountered one? You said a distant past might be survivable.
A distant past, yes. We might survive the immediate event. But survive could mean living on a planet with a drastically altered orbit, maybe chaotic seasons, or increased asteroid impacts due to gravitational disruptions elsewhere in the solar system. Observable effects, certainly. Long-term stability, hard to say.
But not immediate obliteration.
Not immediate obliteration, correct. We'd likely see the gravitational effects, perhaps subtle shifts in star positions or planetary orbits first.
But if it's a closer encounter, the atmospheric stripping kind, or worse?
If it gets close enough for those effects, atmospheric stripping, spaghettification, then realistically there's no chance of survival for Earth as we know it, or life on it.
And it would be.
Silent.
Essentially, yes. The process itself, the tidal disruption, doesn't create a sound wave in space. There's no explosion, just distortion, stretching, silence, and then darkness as the matter crosses the event horizon. It's a very final, very quiet end. Okay, so summing up this whole deep dive, rogue black holes are real. They're out there, potentially in large numbers. They're mostly invisible, and they are capable of utter catastrophe.
That about covers it, yes.
And the really chilling takeaway is that because they're so hard to detect, one could theoretically be heading toward us right now, and we'd likely have very little, if any, warning.
That is the unsettling truth. They're the silent assassins of the universe, in a way. Their existence highlights the sheer scale, the hidden dangers, and the profound unknowns still present in the cosmos.
It really makes you think about how much we don't know, and maybe can't know, about what's drifting through the darkness out there.
It does. While the probability of an encounter might be low in our lifetime, the fact that such objects exist and follow the laws of physics we understand, well, it's a potent reminder of the universe's immense and sometimes terrifying power. Something to ponder, definitely.